Alright, to finish what we started in the last video, we have the other side of the coin for exponential functions, logarithmic functions. And they'll usually take the form f of x equals log base b of x. That's the notation, but we should go over what it means. So if I've got log base b of, we'll say y, equal to x, this means that b to the power of x is equal to y. So we start with the base, we go outside, and then we end up inside of the log. And this fundamentally is all we really need to know about logarithms. This is what they mean. And in fact, if you play around with this definition here and you look at all of the exponential properties, you'll get all of the logarithmic properties. But still, we'll go ahead and go over it here. So if I have multiplication inside of a log, this is going to be addition outside of the log. And similarly, if I have division on the inside, I will have subtraction on the outside. And this property right here is actually really handy in calculus when it comes to circumventing some of the more painful shortcuts, and I'm writing a plus again. Circumventing some of the more painful, what would be shortcuts for finding derivatives, kind of creates a shortcut of a shortcut, depending on the type of problem you have. But something else interesting, I've got, if I have an exponent on the inside, what's a good exponent letter? Let's do C. So I've got a to the power of c inside of the log. And what that happens, that actually comes from my first rule up here. An exponent is a repeated multiplication. And for the multiplication, I turn it into addition on the outside. So this would turn into, this is a repeated multiplication. On the outside, it would be a repeated addition. My c comes out in front as a coefficient of my logarithm. Following suit with the previous section, we've got a couple of special cases here. So if I've got log base b of 1, let's see, this one is always equal to 0. And I'll write another one that goes with this, just because we don't want any mistakes in the future. If I try to take the log of 0, I get undefined. And in fact, the logarithm only exists for positive values, because that comes right up here. I can't raise a positive number to an exponent and expect to get a negative number as a result. Now let's finish this up. Log base b of b will be equal to 1, because this is saying b to the power of 1 is equal to b, which is a true statement. Now, one of the nice properties of logarithms, because you see each of these has a base, actually the base is unimportant. Pretty much all of the logarithms are the same. They all all their graphs are essentially the same, but they're all just a constant multiple of each other. So a handy tool because the original definition is technically all we need to know to understand the logarithm. It kind of takes my exponentiation backwards. I start with a base, I give it an exponent, I get an answer. The logarithm takes the answer and finds the exponent that goes with that base, which is useful when we want to know kind of the size of things or the length of data storage. But a handy tool, because this definition doesn't really help us calculate things. We have a few standard logarithms, namely the natural log and log base 10, well, actually, and log base 2. So a handy tool is the change of base formula. So we suppose we have a log base b of a, but we want it in terms of some other log. So we'll say log base c. Then what we do is we look at what the original logarithm means. So we'll say, okay, we've got log base b of a is equal to x. We don't know what it is. But we look at what it means from the definition. This means that b to the power of x is equal to a. And then what we do is we take a logarithm of both sides. And in fact, we take the logarithm we want. So we take our expression b to the x equal to a, and we take the log base c of both sides. And this is one of those things we can do because the logarithm is going to be a one-to-one function, actually for the same reasons that the exponents were. It's a strictly increasing function. And then what do our log properties say here? Well, this is an exponent inside of a log. That says that the exponent should come out in front of the log. So I have x log c of b equal to log c of a, which means my original x that I never knew is now equal to log base c of a over log base b, log base c of b. So let's fill in. My original x was log base b of a. So if I have an original log, I can change it to be in terms of any other base I want just by lining up the parts in this little formula here. And this is useful, especially if you're using a calculator and you're not using a 50-year-old algebra textbook, because the calculator only has buttons for log base 10 and log base e. Oh, come on, pen. But we don't actually ever write log base e. We write natural log instead. It's French actually. It's log natural, but the calculators will default to log base 10 if you press on the log button. But in mathematics, we typically stick to the natural log, mostly because it only uses 2 letters and it doesn't have any subscripts, so we don't have to write as much. Because of the change of base formula, it doesn't matter what log we're using because we can always change our problem to be in terms of any other base that we want to talk about. So often what will happen is if you are in a textbook, say a computer science class or a math class, and they need to discuss logarithms at some point, they will just simply say log. And usually the context of the class is what decides what base log they actually mean. So if I was in a computer science class and I was reading a textbook and it said log, it started talking about logs of things, then I would understand that since it's computer science, it would start using log base 2. Because in computers, everything is done in binary, and so all the digits are in base 2. If I'm just doing something in regular world, then it's going to be log base 10. But if I'm doing applied math, maybe biology or something, then typically that's going to be a natural log instead. We will deal with more specific examples in the next section, 5.6, when we talk all about solving problems and equations with logs and exponents. But let's look at a picture of what a log function looks like. So we'll use L of x equal to log base 2 of x. If I choose to use change of base on this function to look at it in terms of some other log, say natural log, this would be the same thing as L of x equal to, let's see, the number inside goes on top, so I'd say natural log of x divided by natural log of 2. So because of the change of base formula here, we see that every log function is actually just a constant multiple, because this part on the bottom, this is going to be a number. Every log function is just a constant multiple of some other log function, just by using the change of base formula. You can pull a similar kind of trick, I suppose, with exponential functions, but I think it's less cool. So logs generally take a form that looks like this. They go up. This is assuming that the base is greater than 1. I can talk about a logarithm that has a log less than 1, although you will probably never ever see it, except maybe in this textbook. I don't know why, but we really like to have large numbers for our logs. So when I have a smaller number here, then what's going to happen instead is my function is going to go down. So let me carefully redraw this. There we go. So what you should see when you look at these sideways is they should look like sideways exponential functions. And that's exactly what's supposed to be happening, because this log base 2 of x is the inverse function for 2 to the x. And this log base 1/2 of x is the inverse function of, well, let's keep the words the same, for 1/2 to the x. And we'll spend a lot of time using these as inverses of each other in the next week when we do 5.6. And then everything after that is just applications of these types of functions. At any rate, the logs we have are going to be mostly strictly used as tools to help us solve exponential equations, although the reverse will also happen. The exponential functions will exist as a tool to solve the logarithmic functions. At any rate, the most important portion of this section is going to be the rules of manipulation for logarithms. And when we do next week's videos, we're going to have a slew of examples in how to deal with these within our problems.